Okay, so we'll kind of start here tonight. So get through it, get home then later. But let's see. Basically, I have one more spring problem I'm going to do with you here. Okay, so last time we were doing the spring problems is like section 6.1, 6.2. So we get this around here. Okay, so section 6.1, 6.2. There, hello. Okay, so okay, so spring problems continued here. So spring problems continue. Basically, got one more to do here. Remember, this is kind of the equation here, right? It was m y double prime plus it was c y prime plus k y equals f of t. Can't remember if you use capital F or little f. Doesn't really matter. But I think I use a capital there. Right, like this here, where this m's the mass of the object on the spring, right? It was kind of like a picture. I don't want to draw it all again, but you had the mass here, and then this is called the is a dampening constant, like friction or whatever. And then this was a spring constant here, and this is some external force on it. Okay, so let's say this situation here. Let's say, and by the way here, right, the y. Let me just draw it real quick. Right, so attaining here state equilibrium. Okay, here's the mass, and here's spring constant, and then I think draw like a viscous liquid down here or something like this. And if it's at rest like this here, if this is equilibrium, this is y equals 0 is equilibrium, and then this is positive y here. So like the y goes this direction here. So this is like y equals 0 is equilibrium. If it's just sitting there with the mass on it, and then if you perturb it or something, then it responds and does something there. But anyway, let's say we have, and this is the C down here. But anyway, this we have this here. M is equal to 1 kilogram. C is equal to 0 newtons per meter per second. Okay, and K is equal to 9 newtons per meter, like this. Okay, so that's the information there. And then F of T, let's say there's some external force acting on it. Okay, so it's like being pushed at certain times. Like, so the mass is somehow, it's being pushed or pulled, aside from, maybe pushing on it physically or whatever here, but it's being pushed or pulled. Imagine like a little thruster on it or something, adding extra force to it if you're pushing it or something. Let's say F of T, external force, is like this. Let's say cosine of 3.1 T. Okay, kind of an odd thing here, but we'll see about this in a minute. So some periodic force acting on it here, some external force on it. Okay, so if I fill the things in here, right, I get, and then say initial conditions. Let's say y of 0 is equal to 0, and then y prime of 0 is also equal to 0. So initially it's at rest, it's just at rest at equilibrium, but then starting at time equals 0, there's some outside force acting on it here. So it's sitting right here, and I start pushing it, according to this, the force then. So notice here, this could be positive or negative, right? So, right, so sometimes it's going to be pushing up, other times it'll be pushing down, depending upon the sign here of this at any particular time. So the force can be going either way here, it oscillates the force. So anyway, so if we go through this here, so we got our equation here, right? We got, so M is 1, right? So I got y double prime plus, and then this goes away because it's 0, and then the K is 9. So y double prime plus 9y, right, is equal to F of T over here, cosine of, say, 3.1 T, like this. Okay, so we're looking for the solution to the initial value problem here on this. Okay, and notice this one's, it's non-homogeneous equation. Okay, so the way you start this off, right, you kind of break it apart here a little bit. Right, y is equal to, it'd be like basically Well, if I start with well, yeah, I'll just write it here. So you have your y sub c plus your y sub p, like this. Okay, and the y sub c, that is the solution to the homogeneous equation. If you put 0 here, right, that's the y sub c, the general solution there, plus a particular solution. Okay, so we get y equals, now here then, for the y sub c, if you go through it, kind of off on the side here, right, you get r squared plus 9 equals 0. So then you get like r equals basically plus or minus 3i if you go through quadratic formula or whatever. Okay, so what about this part right here, the complementary solution, right, where this is 0 over here? What would that be? That's going to be like the cosine and sine, right? So that'd be like C1 cosine 3t plus C2 sine 3t, and then plus this particular solution over here then. Okay, so this is the solution to the homogeneous equation here, and then it has the constants on it there, and then we also have this. We've got to find a particular solution then to this. Okay, now for a particular solution then, for yp here, you could use either undetermined coefficients or variation of parameters, right? Can use either method of undetermined coefficients. I'll call it muck. I don't know. Method of undetermined coefficients or variation of parameters, right? So you can use either one of those here. So it's for y sub p here then. And it's up to you which one you want to use here. Probably in general, if you have sines or cosines here like this, generally undetermined coefficients is easier, okay, than variation of parameters. Okay, so you could use either one though. But undetermined coefficients, right, what do you do here? You look for y sub p equals, and if you look at this over here, right, for this one here, what do you want to have like, it'd be like a cosine 3.1t plus b sine 3.1t, like that. So that'd be the particular solution formula you want to look for here then. So I'm using undetermined. I'm using this one here. I'm using method of undetermined coefficients. Okay, so anything there so far? Now, this y sub p, right, that's actually a solution to this up here, right? Because you see, if I let C1 and C2 both be 0 here, okay, then one of the solutions to this is y equals y sub p. So this guy right here, then, it's a solution to this. Okay, so the idea is you want to plug this in. So you take this out, plug it back in up here. Okay, so you plug this back in. So you sub this into the differential equation now. So subbing into the difyQ. Okay, so what we get here then. Now it calls in for two derivatives here. Like when you do this here, let's see. You see sub it in there, and basically you got to find two derivatives here of this. Okay, what you pretty much just do pretty much in just pretty much straight away here. So if I plug this in back up here and take two derivatives, I can do that term by term then, right? So I would get that I get a. Now if I take two derivatives of cosine, it goes cosine, negative sine, and then negative cosine. Okay, so it's going to end up like this. You get a. It'll be a negative there, I guess, and then it goes back to cosine, and then actually the chain rule there. Oh, I gotta watch out. I can do the chain rule a couple times. A little bit messier there. So you get like negative. And you get the a. And you get like a 3.1 squared, and it goes back to the cosine then. Okay, like that. Because every time you take the derivative, it kicks out a 3.1 there, so you'll get this. Okay. Now, how about the next one here? If I take second derivative of the next term, okay, that'd be what? It'd be, or I'm sorry, second derivative of this one now. Okay, that's going to go to negative sign. And you're going to get like 3.1 twice, because every time you take a derivative, it's going to kick out a 3.1 from chain rule. So that'd be negative b times 3.1 squared. I'm just going to leave this 3.1 squared for now, actually. Then sine 3.1t. Okay, and then plus, so that's this part right here I plugged in. Now it'd be 9 times then this right here. So a cosine 3.1t plus b sine 3.1t. See this? Anything there so far, Nat? Okay. I suppose if you don't like the way I subbed that in there, you could just take your two derivatives here. Take a derivative, then take another derivative, and then plug those in. But yeah, so there's two derivatives there of this, and then plus 9 times that. And then that has to be equal to what then? That would be equal to, on the right side, this cosine 3.1t. Let's end up with this here then. Okay, so anything there so far? Now, the kinds of terms you have here then, okay, there's two kinds of terms here, right? There's a cosine 3.1t kind of term. Okay, then the other kind of term is the sine 3.1t kind of term there. Okay, now we'll compare coefficients on it. Okay, so for example here, on this side, I have a cosine 3.1t, and the coefficient would be this. Okay, so here's one here, and there's also another one here. So then when you go through that, right, cosine 3.1t, the coefficient here, that's what? That'd be like negative, I'll say 3.1 squared a cosine 3.1t. All right, I'm sorry, not the cosine there. I'm just comparing coefficients. So you get that. And then there's another one hiding here. If I distribute this here, that gives me what? Distribute this, I get 9a here then as well. Right, so that's the coefficients on the left for the cosine 3.1t. I'm just, again, comparing coefficients here. And what would it be on the right side? 1, right? 1 on the right side. Now you do the same thing for the sine 3.1t. Okay, and that would be what? You get this coefficient here. So that'd be negative b times 3.1 squared there for that one. And then for this, here's 1 here. Okay, but you got to distribute the 9 here, though. And then that would be plus 9b equals, and then what would be on the right side over here? 0, right? So you get 0 here like that. Okay, so anything there so far? Okay, so then you go through this. So you get the a from here, right? So I'm not going to crunch any numbers here, actually. But what you could do here, if you factor out the a, you could factor the a out here. Okay, and then it looks like this. You get a equals 1 over 9 minus 3.1 squared. Like that, that'd be the a here. And again, you could crunch these out, but I want to show you something about this. I'm not crunching them out for a reason here, and I'll show you in the Desmos in a minute, because that'd be the a there. Okay, and then got a little ways to go here, I guess. And then the b would be equal to what? 0, right? The b would have to be 0 here. So the b is 0. So then what we got then? So we got the a and b there. So then I have then what? So for the general solution here, right, I get, so if I kind of recap that, right, I got y equals, it was the C1, go back up here, C1 cosine 3t plus C2 sine 3t plus, in the particular solution, that was this one here, right, from back up here. And we found out the b was 0, right, and then the a was this number here. So that's 1 over 9 minus 3.1 squared, and then I think it was cosine 3.1t, like that. Because that would be the that'd be the general solution there before you do the initial conditions would be this. Okay. Okay, any questions on that so far? Okay, so a little bit of a mess there. Conceptually, it's not too bad, I think, but it's a little bit of a mess with this one, 3.1 there especially. Now, what we got to do next then? To get the equation of motion for the mass here, then we got to apply the initial conditions, right? And that was back up here. I'll just kind of recall back up here. We had our initial conditions here for those things. Okay, so if I apply the initial conditions, maybe I should write them here again, just for reference, right? We had y of 0 is equal to 0, and y prime of 0 is equal to 0. Those are initial conditions. Actually, I guess before I do that, since I have a condition on the derivative there, I want to take a derivative of this here, which I forgot to do. So I want to take a derivative of this now. Okay, so what? So I got y prime is equal to, that would be, how would that go? So take derivative here with respect to t, that'd be negative 3c1 sine 3t plus 3c2 cosine 3t. And the derivative here, what would happen there? That would turn negative now, and it kick out 3.1. So you get 3.1 over 9 minus 3.1 squared cosine 3.1t, like this. Okay, so if I apply the conditions here then, or did I mess up? You're absolutely right. Yep, thank you. Sine 3.1t. Right. I did that on purpose as a pedagogical. They teach that in teacher school to, that way make sure people are, so did that on purpose. Right. Yep. Right. Good. I'm glad you passed that test. Good. So, yeah, actually, that's not what really happened, but that's okay. So here then, what we got, y of 0 equals 0 and y prime of 0 equals 0. Right. So now apply the conditions. So if I put 0 here and 0 in for t, I get apply ICs. So I get 0 equals, and then if I put 0 here, I get the C1, because that would be 1 right here, right? So C1, this would drop, and this would stay, right? So that's a 1 right there, right? That's 1. So I just get plus 1 over 9 minus 3.1 squared. So that's for C1, for the first one there. Now for the other condition, y prime of 0 is 0. So I plug that condition in. So I get 0 equal, now this would drop, this would stay. So you get 3c2, and this would drop over here, right? Because it's sine, so that would drop. So here then I get what? C2's got to be 0. So C2 is 0 there, and the C1 would be the negative of that thing. So C1 equals negative 1 over 9 minus 3.1 squared, like that. Okay, so anything on that? So finally here, for the solution, now I know the C1 and C2. I figured those things out. So I get y equals C1, which is this one, so 3.1 squared, and that was cosine. Did I do cosine first or sine? I don't remember. Cosine 3t plus the C2 is 0, so that will go away. Okay, and then for a particular solution, that was, I forget what it was now. That was, where'd that go? The particular solution. Oh, yeah, that was from this. So that was 1 over 9 minus 3.1. And I think it was cosine of that, and this was 3.1t here, like that. Okay, so you end up with this here then. Okay, so that'd be the equation of motion there for the spring. Okay, so anything on that? Now it's kind of interesting. I want to show you this in Desmos then. Okay, so it's kind of a mess of a problem there. But anyway, if I show this in Desmos, it's kind of interesting. I think it is, if I get this to work the way I think it's going to. Okay, so stop sharing. Safe to stop sharing that one, I guess. I'll stop sharing there. Okay, and consent and join. So just Desmos then. Let me show you this then. So if you graph it, Desmos.com. Let me share the screen here then. Okay, so if I graph it here then, what was that thing? It was y equals, I have it here, negative 1 over, and it was 9 minus 3.1. No, yeah, 3.1 squared. Cosine 3t. Okay, so we have this here. Okay, now that's if there's no, well, yeah, so that'd be like if there was no forcing function on it, it just kind of go like that. But then the effect of the forcing function here, we have that, plus 1 over 9 minus 3.1 squared, and then cosine 3.1t, right? Like this. So this is what it looks like here. Like this would be the motion of it here, then like this. So it's kind of a more complicated motion for it there. So basically, right, that's like if you push on it. So remember, it has a little external force on it now. So if you're kind of pushing at the right times, it's kind of like if you push something in a swing, right? The swing goes back and forth. Okay, but if you push them at the right time, right, they go higher. Okay, and if you kind of push them at the wrong time, you'll slow it down. Okay, so these are just a little out of phase of each other. So it's like you're kind of pushing just at the wrong time, yeah, so you kind of get this interesting thing here. Now it's kind of cool though. I'm going to do something here then with this. So they talk about this in the book a little bit, but these are called like beats. You kind of get these beats here like this. So the spring kind of goes up and it starts shallow and goes up and down a little higher, but it's more of a complicated motion to it. Okay. And if I did what I did last time, I could do the, I can't remember how I did that, but there's a way I could show the motion of it kind of complicated like. Okay. But here's the cool thing that happens then. I'm going to put a slider here for that 3.1. Something interesting here. You notice it's very 3 is very close. 3.1 is kind of close to 3. So that's going to do something. I'm going to put like a C here. I think for a slider. I think I'll let me do it. Wherever I see the 3.1, I'm going to adjust this like a little different frequency, like the external force here. Okay, so I'll add a slider here. Now this slider, I want to run it from, can I change the settings on it? I want to go right around 3. So let's say, like say negative, or let's say 2.5 maybe to 3.1. See what happens. Because here's the slider. Okay. Now let's kind of look over at this part here, over at 0. But interesting here, if I change this, the different things, kind of look what happens to the, if you get closer, not much going on, just kind of wiggly, right? But if you get closer and closer here to 3, okay, look what happens here to the spring. I'm going close to 3. So you start getting these kind of beats in it here. You get closer and closer, they get bigger. Okay, if you get close to 3, then you notice what happens here. It actually starts to, see, it's starting to blow up here like this. Whoops, yeah, like 2 point. We're like really close to 3, like this. Okay, basically what happens is if you push it just the right time, okay, it just gets bouncier and bouncier. It's kind of like if you're going down the road, maybe like you have your shocks in your car or whatever, right? And your shocks maybe not very good, you bounce up and down a little bit. But if the bumps in the road time right with your up and down bumps, right, you can go really crazy. The shocks. So if the frequency up and down kind of matches, if the frequency of the way the car bounces kind of matches the potholes in the road the right way, then you can really damage. Can go crazy, like the oscillations. That's kind of what happens here, where the frequencies kind of match up. If you're pushing just the right, it's kind of like if you're pushing the swing just the right time, everything can make the person go over the top. So it's kind of like that. If you push at the right time, it gets bigger, bigger. Or trampoline, yeah. Yeah, that's a good idea. I never thought of that, but yeah, trampoline's same idea, kind of the same thing there. So yeah, if you give the good push at the right time, you can just, yeah. I'm going to add that to my note here, trampoline. Next time I teach this, there's next time. But trampoline, yeah, that's a good example too, right? So anyway, so that's kind of what happens there. So you can see here, so if you get this if it doesn't match, right? C's don't match now anymore. Okay, the frequency doesn't match here. Now not much happens, but if it's just the right time, if you do it just right, it gets closer to that, it starts to get crazy like that. So, but anyway, and you get these like beats like this here. So, but if you get right at 3, it just blows up. Okay, but if you kind of move away from it, you get these extra little things like this here, and so on and so forth. But like that. But if you get closer and closer to 3, right, the motion just kind of blows up there then. So, okay, anything on that? I just want to show you that one. So, so let me switch back here then. Okay, so if I go back here, shares, cancel, share screen. Wait, okay, I'm gonna stop sharing here. Okay, and okay, so go back to this thing. So, okay, so that's pretty much the end of that section I had. So nothing really more in that section. Okay, so that's kind of the spring problems there. So it kind of matches the homework, but it's close to the homework like that. So, and I guess I'm going to go ahead and start the next section then, since you guys are here and it's raining out now. So, okay, since you guys are here, but any questions in that? Okay, so it'd be kind of cool to show it. Remember that last night the other night I had the bouncy ball kind of thing there. It'd be nice to show the bouncy ball with it. You can kind of see what it would do, but you get the idea though on it. So, okay. So we're just going to start the next section here. I don't know how far we'll get on this, but let's see. So this is section 8.1 here now. So zoom in here a bit. Okay, and this is a big chapter. Talks about what's called Laplace transforms. Okay, so the Laplace transform here. Okay, so definition of it first of all. So kind of a lot of stuff here with this. A lot of notations and things. It's kind of hard to explain unless you go through some examples, I think. Have you guys ever seen this before? Maybe Laplace transform? Probably, maybe not. But it's just the first place you see it. But anyway, I'm just going right to definition. So I'll start with definition. I'm going like a script L here. Okay, it's kind of a script L like this. So you see its notation sometimes. And we're not going to really get to differential equations to this for a couple classes, but it was kind of used to working with the transforms a little bit. But it's like this here. the Laplace transform of a function. Okay, it's actually defined by an integral, like this. Okay, so this is the definition here. I'll put this in a box right here. Okay, and yes, we got this here then. And basically, by the way, this is an S. Okay, this is an S here. It's like S. So the answer could have an S in it. Okay, I think the easiest way to do this, let's just take an example, find a Laplace transform of something. Let's say, find this one here. Let's say the Laplace transform of 1, for example. Say the Laplace transform of 1. Basically, we just kind of follow the definition here. Right, so you get this will be what? Integral 0 to infinity of what? E to the negative st times what? Times 1, right? Because, right, so it's like times 1 here. Okay, so basically now it's just a matter of doing this integral where the s is a constant here in this. Okay, well, what you could do here then, I don't know if you remember in Calc 2, we did improper integrals a long time ago in Calc 2, improper integrals. Remember what we did? We put like a b up here and then take a limit as b goes to infinity and blah, blah, blah. Okay, we're going to kind of skip that part and just leave the infinity here and do it this way. Basically, all you got to do here in this, find the antiderivative and put it in the brackets. Okay, so antiderivative of this. Now, you notice here, you're taking antiderivative with respect to t. Right, so s is just a constant. It's just a constant here, right? So you're taking antiderivative with respect to t. Okay, so how would that go then? So imagine, say I had this, for example. If I ask you to find antiderivative of this, right, that'd be like this, right? It'd be e to the negative 3t with a negative 1/3 in front. Okay, if you did antiderivative of this one. Okay, so in our case then, yeah, so it get e to the negative st like this over, and then over s, I can put a negative in front maybe here then, like this, or over negative s, you could say. Maybe, whatever, I could think of it down here like that. Or so that'd be the antiderivative there. But then we have these limits here, okay, like this. Okay, so and maybe I'll write it another way here too. Let's try it like this: negative 1 over s e to negative st. Now this s can be really annoying because it looks like a 5. So you gotta be careful with these s's here. I don't like the s in this, but that's the notation for it. But anyway, try like this. Now you put in your upper and lower, right? So if you put in the upper here, now what happens if you put in infinity here? If you put in infinity, what would this become here? If I have, yeah, we'll assume s is greater than 0, right? We'll assume here s is greater than 0 in this, because right, if s is greater than 0, then this goes to infinity. That goes to this goes to 0 here, right? Because that'd be 0 in the upper minus, okay. Yeah, actually, I'll leave that off for a minute here. And then minus on the lower, what would that become then? So minus in the lower, if I put in 0, what would I get? Yeah, 1 over s, right? Or negative 1 over s, like this. So you end up with this right here. Okay, so then this is equal to 1 over s. Okay, so that's 1 over s here then. Okay, so 1 over s. So that would be the answer here then, is 1 over s. This is assuming here, by the way, that s is greater than 0, right? We assume here in this s is greater than 0. Because otherwise, right, s has to be greater than 0. Otherwise, this will blow up here, right? If s were a negative number and you have to go to infinity, this will blow up to be very big then. So we're assuming here s is greater than 0 in this. So what you can say here then, the Laplace of 1 is equal to 1 over s, like this. Right, so the Laplace transform of 1 is 1 over s. Okay. Now, a couple notes here. I'm not going to write the s greater than 0 here anymore. So we'll just assume s is properly restricted. Okay, so just as a note here, I'm not going to write that every time, but we'll assume s is properly restricted, I'll say. It doesn't really matter for any calculations as we go here. Okay, so I don't want to belabor that. So Laplace of 1 is 1 over s, like that. Okay. Now some notations here then. With the Laplace transforms, a lot of different ways to write it. You could write this here, the Laplace within the bracket here of f of t, these brackets. So you could write the Laplace like this. Another way you see it written in the book is just like this here. There's different ways to write it. So they might just say the Laplace of f, like that. So that's another notation you might see. It means the same thing here. And then another notation is capital F of s, like this. Okay, so these all mean the Laplace of f of t. So it's this bunch of different notations here. So it's like basically three different ways you could write it, okay, for the Laplace transform. Okay, so the Laplace of f of t can write like this, or it's capital F of s, you could say. This is like capital. You have little f. It's like you have little f of t and then big F of s. Okay, so and then these two together here, if you have f of t and capital F of s, okay, this is called a transform pair. They go together, basically. So it's called transform pair. So if this is like 1, then that'd be 1 over s. So you can write them as a pair like that. So example, okay, 1 goes to 1 over s, for example. Okay, so there's just different ways to write it here, like that. So the Laplace transform of 1 is 1 over s. So, okay, but anything on that so far? Okay, let's just go through another example. A couple more. We'll do a few of these. We're going to do a few of these with see how far we get with this tonight. But got that here. Next up, then. Let's see. Let's try this one here. Find the Laplace of, let's say, e to the at. And by the way, we're going to make like a little catalog here as we go. I'll put these in boxes as we go. So the Laplace of 1 is 1 over s. So we're going to make like a catalog here as we go of this. So let's try this one here now. Laplace of e to the at. Okay. And then what? So that'd be 0 to infinity. Definition is e to the negative st. And then now our f of t here, there's what? It's this e to the at. Okay, like that. So that'd be the definition of it there. Okay. And then we just got to work in the integral here. So this would be then, well, if I clean this up a little bit here, it'd be integral 0 to infinity. And by exponent rules then, right, that'd be what? E to the, see if I get this right, that'd be, I'll say a minus s. Is that how you do it? Or, okay, I'll say, I'll write it this way. Negative s plus a t. That's just by properties of exponents. You could write like that. So this is by definition here. And then got this. And now we can do, this is just a constant here. Remember, integrating with respect to t. So this is constant. Okay, so then what that'd be, I could do bracket here. And this would be e to the negative s plus a t over negative s plus a. Infinity and 0 here. Okay, so anything there so far? Now, if you go through this, then let's see. Well, if I put in, yeah, let me just do this. If I put in infinity, I can do that here. So if I put in infinity, what would I get? And we'll assume this is right here. Assume this is a positive number here, this s negative s plus a. So if I put in infinity here, what would that be? I'm sorry. Assume this is a negative number. Assume this is a negative number here. So if I put in infinity, let's see. Wait a minute, I got to think there for a minute. I need negative s plus a has to be less than 0. So yeah, if I'm multiplying through by -1, that'd be s minus a is greater than 0. Okay, so s would have to be greater than a. So if you assume here s is greater than a, okay, but what would this be here? Assuming that this, if I put in infinity, assume this goes away. Assume this part goes away here then. Okay, so if this is, let's say that s is greater than a, right? Assume s is greater than a here. So if s is bigger than a, okay, that makes this will be a negative here then. Okay, so what would this be? If I put in infinity, that would go to what? That would go to 0, right? It would go to 0 here for the upper, like that. If I assume s is greater than a, okay. Yeah, okay. Right, because if I assume s is greater, here's the way to think of it. If I assume s is greater than a, that means s minus a is greater than 0. Right, so that means negative s plus a is less than 0. So assuming this is negative here, right? So assuming this is a negative, okay. So, and what would be here if I put in 0, then what would I get? So negative, that's, if I put in infinity, I get 0. If I put in 0, then what would that be? This is just 1, right? That's just 1 up here. So you get 1 over negative s plus a, like that. And if you clean this up here, then that's going to be the same. Actually, I can take that negative and kind of take it down here and distribute it. Okay, so you end up with this here. It's 1 over s minus a, like that. 1 over s minus a. And that's assuming here s is greater than a. Okay, so that would be the Laplace then of this. So the Laplace of e to the at is equal to 1 over s minus a. Okay, so I'll put this in the box here. So for example, what would be the Laplace of e to the 3t? So if it's e to the 3t, the Laplace of e to the 3t would be what? 1 over s minus 3, right? Yeah, right. So that's the example there, right? So the a can be any number there. That, and again, we're going to assume we have the right restriction on it here, so I'm not going to worry about this part so much. But yeah, so end up with that. Okay, so that's the Laplace of that one. Anything on that? And make a note to myself. I clean it up next time. Let's see. Okay, let's get that. Okay, so that's that one there. On to maybe another one here tonight. We'll try to get through one more at least here. Let's try this now. Let's find the Laplace transform of t squared. Okay, so Laplace transform of t squared here. Okay, this makes a bit of a mess here, but on this one, what that'd be integral 0 to infinity of what that'd be e to the negative st right, times what? So looking for this one now. So Laplace of t squared times t squared. T squared dt. So you get this here. Okay. And this integral, a little bit messier. Unfortunately, this is integration by parts. Here, this one. Okay, so you get integration by parts here. So here then, I'll just kind of go through the tabular method for this. Like we talked about, I think we did maybe in here a little bit, but make the table thing. So you can go like this here. T squared e to negative st. You take derivatives going down here. I can't remember if I did this in this course or not, but I think we did once earlier. But for integration by parts, you go down here. And then now this would be what? This would be, it'd be e to the negative st over negative s, I guess like that. And what would be the next one then? It'd be e to the negative st over what? S squared, right? Because you bring another negative s down, that just becomes s squared. Okay, and then if I do one more here, that'd be go to e to negative st over, that'd be negative negative s cubed, right? Like this, okay, like that. Now, if you do this thing here, right? Go like this. Okay, and you have positive, negative, positive. Okay, so if we go through that, then so now I can go to the bracket here now because I can basically write down the antiderivative. So that would be what? Negative. How do I want to write it? Negative. I'm going to kind of write it this way: 1 over negative 1 over s t squared e to the negative st. That's that one. And next one would be what? It'd be minus, got a minus there now. Then 2 or 1 over s squared. I don't know why I wrote in this order. Times, or actually it's a 2 over s squared, I'll say. 2 over s squared, and then t e to the negative st minus, it's a minus here again. Now it's what? 2 over s cubed e to negative st. Okay, infinity and 0. Okay, so you got that. Okay, and I want to check something real quick on this last one. Did I make a boo-boo? No, I guess not. Okay. This is the way that worked out. Okay, so anyway, now here then, now we'll assume here s is greater than 0 on this one. So that way, you know, if I let, now what happens if I put infinity here for these? So if I put an infinity, what about this one here? Yeah, actually it's not obvious, but this one, this will take care of this one here. This e to the negative st. It's like a competition here on these two actually, but this one will go to 0. And this goes to 0 much faster here. If you did like L'Hopital's War or something, okay, this goes to 0. That one goes to 0. This one goes to 0. That goes to 0 in the upper. Yeah, what's that? They all go to 0 in the upper. Yeah. Okay, now in the lower, I put in 0 there. Actually, yeah. What happens here? This goes to 0 because if t is 0, that goes away, right? And this goes away. This one stays though. Over here, that last one. So you get like just minus 2 over s cubed, and then I get 1 here if I put in 0. So end up with this. So this is equal to 2 over s cubed, like that. Okay, so the Laplace transform of t squared, try again there. I hate those brackets, I can't draw those, is equal to that's 2 over s cubed, like that. Okay, so anything there? Now, actually, I'm not going to put that in a box yet. You could generalize this. You can do t cubed, t to the 4th, t to the 5th, and so on. It'd be the same idea, more messy. Okay, in general, it goes like this. I'll put this in the box. So the Laplace transform of t to the n is equal to n factorial over s m plus 1, s raised to the m plus 1. This is the general result here. We did it with 2 there, but if you did it with 3 or 4 or 5, this is the general result you get for it. So that's the Laplace of t to the n, where n's a whole number, 0, 1, 2, 3, 4, and so on. Okay, so anything on that so far? Okay, now we're kind of get away from the definition now a little bit. A couple others here, I won't go through them, but another one here, the Laplace transform of sine of at, it comes out to be this, a over s squared plus a squared. Oops, let me check here real quick. So we got that. And the Laplace transform of cosine at, if you go through the definition, it makes a mess because you got to do integration by parts and solve for the integral. It's a mess. But anyway, this one is s over s squared plus a squared, like that. So we're kind of building up this catalog here. And by the way, I think on my open math, there's actually a table. There's a table there of different Laplace transforms. So this will appear in a table eventually. There's a nice table you can have of these. But this one is this. Okay, again, it's all from the definition. You can go back to the definition of the integral thing and do all that. Okay. Now some other things about Laplace transform. The Laplace transform is a linear transform. Let me see here. It's called a linear transform. So you actually get some other properties here then. This is also true here then. A couple others. So say that the Laplace of a times f of t, like this. Okay, you take the a out. So there's this property here. Okay, and then the other part of linearity here would be this. If you have, say, the Laplace of a sum of two things, like the Laplace of a sum, okay, that's the same as the sum of the Laplaces. You can take these you can take these separately here. Okay, so anything else so far, Nat? Okay, so I'll put these in boxes here, these two. Okay, so for example, let me give you a couple examples there. So for example, then, let's see if I find the Laplace of this. So the Laplace of 3t to the fifth plus 7 sine of 2t. Okay. Well, according to these things, then what you could do, I can take the 3 out, right? So I could break it into two pieces here. And so for example here, let me just write this down. I think this will work. So I can put the 3 here right away. So 3 times, I can take the Laplace of this then. So Laplace of t to the fifth, that was Laplace of t to the fifth. That was, was it? It was 5 factorial. That's going back to the other one, right? So 5 factorial over, and then it was s, and then s to the 6th. Is that right? Because it's a plus n plus 1. So 5 factorial over s to the 6th there, plus 7 times, now the Laplace of sine of 2t, okay, that was, I think that was, it'd be 2 over, was it a over, get these back here, that'd be 2 over, and then what, that'd be s squared plus 4, right? Right, so that'd be the Laplacian of this one, right? The Laplace of this one would be this. For an example there. So you don't have to go back to the definition every time once you get these rules. And these are nice here, they're linear. Okay, another example of that, let's say the Laplace of 9, for example. So Laplace of 9, according to this then, basically think of it, that's just like the Laplace of, say, 9 times 1, for example. Okay, so that would be basically then the 9 can come out, okay, because it's constant. What was the Laplace of 1? That was 1 over s. So for example, then you could write this, right? The Laplace of 9 would be 9 over s, for example. You don't have to write this every time here, but if you see Laplace, want the Laplace of 9, it'd be 9 over s, for example, there. Okay. Anything on that there? Okay, now one other theorem here I'm going to try to get through here today. Well, this won't take long since you guys, there's one more theorem. It's called the first shifting theorem. Okay, goes like this. It's easy to show it in examples. So for example here, let's say we'll find the Laplace of e to the 7t, say cosine 8t. Okay, and basically what this says is here, you take you kind of ignore this for a minute. So just ignore the e to the 7t for a minute. You take the Laplace of this, okay? So you take the Laplace of, say, cosine 8t, right? So that would be, what that'd be, may not quite write this down yet, but just watch this for a minute, maybe. So cosine 8t is what? That is, that's s over, that'd be s squared plus 64, right? And what this says then, this e to the 7t in front, you take the s then, in this case, the a is 7 here. Okay, so the a is 7. So what you do here, you take the s, you replace it with s minus 7. So I put s minus 7 here, and then also here, s minus 7, like that. Okay, that's the shifting theorem, how it works. So basically, you find the Laplace of this here, but then you take the s, replace it with in this case, s minus 7, like that. So that's how that works. Okay, another example of that. That's a little kind of weird there, but basically the e over here causes a shift over here, right? So the e here on this side, it causes a translation in the s over here. Okay, another example. Let's say the Laplace of t. Well, I'll just write it this way. Say the Laplace of t cubed e to the negative 2t. Okay, So basically, you start by finding the Laplace of the t cubed, okay, which is what? That's 3 over, yeah, it'd be 3, is it 3 factorial? I'm sorry, 3 factorial over, was it s plus, it'd be s to the fourth. But instead of s to the fourth, you write this now. Now, actually here, the sign switches as well. It'd be like this. A lot of little things to keep track of there. Does that make sense? Right, because right, the t cubed, that's the 3 over s to the fourth, and then this e to the negative 2t here, it causes a shift. And notice here, there's a sign switch in this, right? If it's a here, it's negative a here. So if it's as a positive here, you're subtracting it over here. And then if this were like a negative number, you'd be adding it here, because that's what's happening here. That e to the negative 2t becomes a plus 2 there. Okay, so that'd be that one, for example. So that's the effect of multiplying by the e to the, it causes that shift like that. But there's also a sign switch there you got to watch in that. Okay, so one more example here then. How about this? Let's say the Laplace of 7e to the negative 2t plus t, for example. Maybe trace yourselves for a minute. See if you can figure this out. Okay, so maybe here should be this. It'd be so the Laplace of 7, that'd be 7 over s, right? But I had that shift, I got this thing here, so it'd be 7 over s plus 2, right? Plus, and then the Laplace of the t, that is the it'd be like the 1 factorial over then s squared, like that. Okay, so this would be the answer here, like that. And the 1 factorial is 1. You write 1 here, but it'd be like that. No, because the e was only on the first one. Yeah, so yeah, just be on the first one there. Okay. Okay, good. So anything on that? Okay, so yeah, I guess that's good work for tonight, I think. So we'll kind of leave it there. I got a little bit more to do with that. And then next time we'll do one more, then we'll probably start inverse Laplace transforms. That's going the other way. So it's not that bad, but it's just doing the reverse process kind of thing. So we'll work on those next time. Okay. Oh, I guess one thing I should mention too, I'm kind of looking at a test coming up. I'm thinking a week from Tuesday. Okay, it's not this coming Tuesday, but a week from. Okay, for test number 3. Okay, I think I want to do it before we get too far into the transforms, because I'm thinking a week from Tuesday for the test. So I'll get something posted over the weekend here for it. But basically, it would be the second order stuff, second order equations, basically undetermined coefficients, variation of parameters, and the springs. Okay, so it'd basically be those 3 things, I think. So, okay, so any, and I'll get more posted about that soon. But anything on that? Okay, so it'd be, I'm thinking, yeah, April 7th. Yeah, that Tuesday. So, and we'll do review next Thursday, a week from today. We'll do review. So it'll just be review day next Thursday. So, but on Tuesday we'll keep going for Laplace stuff, and then we'll do review on Thursday, and then okay. So.